Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, we think we've got a good show for you today. We're going to cover this topic: controlling a smart motor with a Horner OCS over CANopen. So on this channel, we've showed you a few times how to interface stepper motors and other smart motors to the Horner OCS. Today, we're going to show you how to do it over a network, specifically CANopen. And to bring in to talk about this topic and also to make an announcement, we're going to bring in our product manager, Mr. Casey Gardner. How you doing today, Casey?
Hey, I'm doing good. How's it going, Chuck?
It's going terrific. So traditionally, we've supported CANopen with our XL series products, either as a master or as a slave, but it hasn't been supported in all of our products. You've got an announcement to make as we're expanding our CANopen support.
Yeah, as you mentioned, basically we are expanding it into our micro OCS series. Basically, it's going to be a licensed per unit feature. So for about $100 per unit, that will be something you can add to basically have more advanced communications. And part of that will actually also be adding BACnet IP support for the micro OCS, as well as OCS-IO communication support as well. So the BACnet IP will be a licensed support feature as well. And this will all be through a firmware release coming soon in April.
Awesome. So that's 3 in 1. So again, BACnet IP is building automation and control over Ethernet. So we'll be a server in that scenario. And again, you'll be able to license your micro OCS as a one-time upgrade to support BACnet IP. Same thing with CANopen, a one-time field upgrade. And of course, OCS-IO support's just adding that native capability to the product.
Absolutely.
Excellent. All right. Well, thanks for letting us know about that. That's a big deal, and we're looking forward to that release in April. Okay. Let's take a look at how we're breaking down today's topic. All right, we're going to do a quick review of CANopen. We're going to talk about different applications where you might use CANopen with OCS. We're going to go back to the basics with CANopen. And of course, we're going to have plenty of demonstrations, whether we're talking about configuration in Cscape or whether we're talking about bench type demonstrations. All right, here we go. Before we start, I do want to mention we've got a couple of excellent live streams that are available on our YouTube channel that we did last year. I would especially recommend the CANopen Networking How It Works for those of you just getting started with CANopen. We think it'll give you a good baseline of knowledge for you to kind of understand how things work. And then the hands-on session was good as well. With that one, we showed you how to connect a CANopen-based encoder to an OCS. All right, now let's do our quick review of CANopen. What is CANopen? Well, CANopen is a standard communications network. It's effectively a field bus network that's based on the CAN chip. Now, there are plenty of networks based on CAN. You've got J1939 in mobile and automotive applications. You've also got Horner's own CsCAN network, which is used for adding I/O to OCS, or even for having OCSs communicate with each other over the network. Now, as we compare CANopen with CsCAN, they really were designed with two different things in mind. CANopen is really a standards-based network geared around having components from multiple manufacturers talking to each other, whereas CsCAN was geared around getting Horner components to connect in as easy a fashion as possible, purely a plug-and-play approach. So two different approaches for CAN networking between CANopen and CsCAN. Okay, so why would you use CANopen with OCS? Well, interoperability is what CANopen is all about. So if you've got a sensor or an encoder or a smart motor that you want to communicate to, CANopen could be an excellent choice. It's really good for motion control because it has a lot of capability at a pretty low cost when you compare it with other networking choices. Now, if you're just talking about adding I/O to an OCS or having OCS communicate with each other, really CsCAN is the way to go because it's purely a plug and play type scenario. So now let's talk about what your options might be if you're going to interface a smart motor with an OCS, because most smart motor manufacturers do have a variety of choices. Now, let's start though by talking about why a smart motor and an OCS are such a great pair. Well, if you take a look at the level of integration on an OCS, you've got a logic engine with built-in I/O, operator interface, and networking in one compact package, all configured with the same software package. If you take a look at smart motors, you've got your motor, your drive, your networking interface, all built into one component. It's also highly integrated, so it doesn't take a lot of complex integration, certainly not electrically, to interface these two components and to really provide a complete system with a minimum of components. Okay, now we're going to talk about your different options when you're interfacing a smart motor with OCS, because you could use kind of the old-fashioned step and direction approach. You could go with a Modbus serial approach, and those will both work well, and they'll be fairly cost-effective. But if you're looking for, let's say, the next level of performance, then CANopen would offer that at a modest cost increase over maybe step and direction or Modbus, and maybe priced the same. Now, you've got some other options as well. In some cases, you might think maybe a little bit easier options from a configuration standpoint, especially when you're talking about Modbus TCP. However, those options generally come at a premium. When you look at smart motors, you'll find the Ethernet options are more expensive than CANopen. Now, which controllers support CANopen? Well, for years, built into our two CAN port versions of XL series OCSs like the XL7 and the EXL10, those have supported CANopen as standard, and that remains. So if you've got an EXL10 or an XL10 Prime, or an XL7 or an XL7 Prime, those have CANopen available on the second CAN port. Now, you can order CANopen as a factory option for all the XL series and XL Prime series products that have a single CAN port. Okay, because there's only one CAN port in those products, you have to order CANopen from the factory. That's also true for the X5, which currently, until the next firmware update, is the only micro series product that supports CANopen. And as Casey mentioned in the opening, we will be making CANopen available as a field upgrade, a one-time field upgrade per controller for the rest of the micro OCS line. Okay, now let's get into some CANopen basics. Let's talk about some nomenclature and kind of tell you how CANopen works. So let's start with the object dictionary. Well, the object dictionary is really nothing else than really just a list of parameters. That's how you can think of it. A lot of variable frequency drives, for instance, that have Modbus support, they'll have a list of their parameters along with a list of Modbus addresses. So this is kind of analogous with CANopen. One thing that's a little different with CANopen, and that is CANopen uses hexadecimal addressing, and it not only has an index, which is the equivalent of the address, but it also has a sub-index. So it's organized just a little bit differently. Now, one of the really nice things about CANopen is that it has what's called device profiles. So depending on the type of device that you're integrating, there's specifications that detail how that type of device should interface over CAN. So, as an example, you'll find that there is a profile called CIA 402, which I've highlighted on the list there, and that covers drives and motion control devices over CANopen. And that's where you would find smart motors from a category standpoint. So even though I'm going to be showing you today a nanotech smart motor, you're going to find that the interface is going to be very similar for other brands of CANopen smart motors. So that's a real advantage of CANopen, the fact that these device profiles standardize how similar devices communicate on the network. So now let's dive into some of the different message types or protocol types that are available as part of CANopen. Let's start with network management. What is network management? Well, network management is a way for the current state of the network to be managed. It's most typically managed by the master on the network, which is, in the application we're talking about today, a Horner OCS. But the network state can be one of several different choices. When a network comes up, it's in the initialization state. then it's pre-operational, then it goes operational, which is where it does most of its work, if you will. It's the equivalent of run mode. And then if something goes wrong, the network will go down and effectively will be stopped. So that's network management. So again, you do most of your work in the operational phase. Heartbeat protocol, what's that all about? Well, that's used as it sounds to determine the health of individual nodes. So that's a protocol that's used over CANopen for that purpose. And then you have a couple of different types of messages that are used to exchange data. You have something called a service data object, or an SDO. Now that's the message structure that's used to transfer as needed type messages. So they're not set on a continuous basis. Maybe you have a parameter you just need to change on an occasional basis. You can use an SDO for that. And then you have process data objects, or PDOs. Those are continuous data exchanges that occur while the system is in run mode or operational state. And that's where, in most cases, a bulk of your data is exchanged. Now, one other protocol I want to talk about, and that is something called the sync protocol, and we're going to be demonstrating that today. The sync protocol is an option you can use, you don't have to use it, which allows typically the master to send out a sync pulse periodically, which will allow PDO type messages to be exchanged on a periodic time schedule. Maybe every 50 milliseconds, maybe every 10 milliseconds, whatever the case may be. So that's the sync protocol that's available as an option. Now let's talk about CANopen configuration, specifically, or this is more of a general purpose set of recommendations, but then we'll get more specific as we get down to SmartMotors at the end, and I'll show you how to do it in Cscape. Okay, so here are my hints for keeping CANopen configuration as straightforward as possible. First of all, start out by configuring just the basics. And once you've got the basics working, then expand it from there. Don't try and do all the configuration all at once. Do the base amount of configuration, test it, make sure it's working, and then move on. If possible, use the default settings on the client for baud and ID. So for instance, let's say your application is you've got one OCS and one SmartMotor, and to make things easy, whatever the default baud rate is for that SmartMotor and the default ID for that SmartMotor, just use that. That keeps things simple, all right? Also, before you start, you always need to make sure you gather all your documentation for especially the SmartMotor. Okay, make sure that you've got the documentation, you understand what's included in the documentation, and also you're going to want to gather EDS files, which are a special file that you'll use as part of the CANopen configuration, which will really make it a lot easier to grab the data that you want from your SmartMotor. So the basic process that I'm going to show you and demonstrate here in a couple of minutes is as follows. And I'm not going to show you, I'm not going to, verbally go through every single step because I'm going to be demonstrating this here in a minute. But effectively what you're going to do is you're going to select your baud rate and your CAN IDs, map those out. You're going to make sure you get your EDS files gathered up and copied into the appropriate directories. If your slave that you're configuring, like a SmartMotor, if it has its own software for configuration, you're going to handle that first. And then once you dive into CANopen configuration on the OCS side, which of course uses Cscape, then you're going to have a series of steps we're going to go through. And again, instead of reading those to you one by one, I'm going to go ahead and demonstrate those for you here in a minute. And again, the key is to configure a certain amount of items and then go ahead and do the testing. Okay, now when you're talking SmartMotors, because of the fact that there is standardized profiles available in CANopen, one of the beauties of CANopen is the fact that a lot of the data addresses are standardized. So when you're talking about interfacing an OCS with a SmartMotor, especially if you're talking about positioning control, maybe you're going to move an object across the x-axis or something like that, then you'll find that the data is going to be the same from application to application. So what I've got here is kind of some of the data that is going to be important for a typical positioning application with CANopen. Now there's literally hundreds of parameters available. I'm showing you the ones that are the most requested or the most required typically. So next, let's go ahead and fire up Cscape, and I will show you how to configure a smart motor. Okay, so what I have here in front of you right now is I have an application I'm going to review with you shortly that's already configured. But let's go ahead and open a new application, and I'll show you how to do this from scratch. So I'm going to select new. I'm going to go ahead and use a register-based approach for this particular example. You could certainly do it in a variable-based approach, but I can demonstrate the register-based a little bit quicker, so I'll go ahead and do that. Okay? All right, so we've got a new application that's blank. We're going to start from the configuration area. Now I'm configuring an XL7, and one of the beauties of the XL7 is that you have CANopen support available as standard on port 2. So I'll select CANopen on port 2. I'll hit the configuration button. Now, an OCS can act either as a CANopen master or as a slave. When you're dealing with a smart motor, the OCS is going to be the master, so I'll select that. And then we get into the configuration. Okay, so let's get started. All right, so we're going to start by configuring the OCS as a master, and then after we get to a certain point, we'll go ahead and add in the slave, which will be the smart motor. Now, in my hints, I recommended that you use the defaults for ID and baud rate for the slave that you're using if those will work for you. So the default with the Nanotech smart motor is an ID of 1, which means I don't want the master to have an ID of 1. So I'm going to go ahead and assign a 127 as my master ID. That's very typically done actually for masters in CANopen. The default baud rate for my motor is 1 megabit, and as long as my network's less than a few meters, that's not going to be a problem, and my network is, so I'll go ahead and do that as well. Now, in terms of what I need to configure, I'll just show you. Now, generally, you're going to configure the minimum. So one thing that we do want to check is the perform NMT start all. What is that about? Well, that's that network management I talked about. So the OCS as master is going to be responsible for the network state, and so we want the OCS to automatically start the network to put everything ultimately into operational mode. So we make that check mark. The only other thing we're going to want to configure here is a status register. We definitely want a status register, so I'm going to assign %R1 to that. Now again, I am doing register-based logic here. And how many registers will this require? Well, it will require 4 words, or 4 consecutive word type registers for the master. And then for every slave I add later, I'm going to have another 16-bit word as well. Okay, but I haven't added any yet. That's why that says 0. All right, now there's plenty of other things to configure. Let's go through that. All right, so under device type, that's just informational, nothing to configure there. Under special function objects, I only need to configure special function objects if I'm going to take advantage of the sync protocol. Remember, the sync protocol is an optional approach where the master can effectively send out a sync pulse periodically that all PDO messages are timed with. And in my example application, I'm going to take advantage of that. So I want the master to generate the sync message. Then all that is left for me to configure is how often the sync message goes out. So by default, it goes out like every 500 milliseconds. That's way too slow for me. I want to go with 10 milliseconds, which is 10,000 microseconds. And then finally, we have to configure what portion of that 10 milliseconds do we want to send sync messages in. And I'm going to make it the first half, or 5,000 microseconds. Okay, so that's all we need for special function objects. Under error control, I don't want to use node guarding. That's a little bit old-fashioned. I want to use heartbeat, okay? And I want to generate a heartbeat every 500 milliseconds. All right, now later I'll come back in and add in a configuration time, or a heartbeat time, for monitoring the heartbeat of the smart motor. But since I haven't added the smart motor yet, I can't do that yet. Okay, so nothing to configure under SDOs, and then we have PDOs. Now, remember, PDOs are the messages that we're going to exchange at runtime. So the only configuration I'm going to do right now on PDOs with the master is I'm going to add a couple of transmit PDOs to the master. Why am I doing this now? Well, you can't map data in and data out from device to device on CANopen until the device that's transmitting the data has effectively been configured with at least its transmit PDO. So I'm going to go ahead and add 2 entries here for transmit PDOs. I'll hit the button the first time. I don't want a disabled PDO, so I'll uncheck that. Now, under the object ID, that's what this stands for, I just want to use the default value for as much as I can. So I'm going to use the default value for my object ID for this transmit PDO, and I'm going to go ahead and make this transmission signal to be based on the sync pulse. So every time there's a sync pulse, that's when I'm going to transmit this PDO. And then I'm going to add another one that is effectively identical to what I just created, with the only exception that its object address is slightly different. I'm still using the default, so I just copy the value from here to here. It's still synchronous and based on a sync pulse. And now I've added my transmit PDOs for my master. Now, you could have many more than just 2 transmit PDOs, but for this example, this is a good place to start. Okay, so we've pretty much configured the master, at least with as much as it needs to be configured for now. Let's go ahead and add our smart motor. So I'm going to do that by hitting the Add Slave button here, and then that kicks off a slave configuration wizard. So what's my node ID of my slave? It's going to be node ID 1. That's the default for my smart motor. And I'm going to load the slave from its EDS file. So I've got the EDS file. I previously loaded it into Cscape in the appropriate directory, and so I'm going to go ahead and utilize that. So I'll hit the next button here. Okay, I do want to use the default settings for sync. I don't need to do anything with time stamping. The default settings for emergency protocol are also fine. I won't be really using that, but I'll just leave it at default. And then from a heartbeat standpoint, just like the master, I'm going to have the motor generate a heartbeat every 500 milliseconds, and I'm going to check from the master node, which is 127, I'm going to check to make sure I receive a heartbeat from that master mode at least once per second. Okay, so that's how I want to configure my heartbeat monitoring. All right. I do just want to have the standard object IDs supported for SDOs. I don't need to do anything special there. I do want to have a couple of transmit PDOs with my motor. Okay, so I'm going to set that at 2. I could go up to 4 probably. I'll use the standard object IDs as much as possible. Now, in my case, I don't prefer to use global addresses for mapping data back and forth. I prefer just to use standard %R registers, so I'm going to uncheck that option. All right. I do want to be able to receive PDOs from the master in this case. Remember, we're configuring the smart motor. And again, just like on the data going the other way, I typically like to avoid global data. All right, so I'll hit the Finish button now. And now I hit OK. Oh, there we go. I was waiting for that EDS dialog to pop up. So now I can select the manufacturer of the device I'm adding, and that's Nanotech. The device is the PD4. That's the model I'm using. And profile is the only one available there. Okay, so I'll say OK. And now my Nanotech smart motor has been added. So now we can go through and configure the details for that. Okay, so let's get started. Starting here, we're going to make this a mandatory slave. What does that mean? Well, that means is that if this slave is powered down, for instance, we're not going to send the CANopen network into operational mode because there's no point. A critical slave is not up and available. So that's what mandatory slave means. Now, in terms of this section here, these are all the different services, if you will, that we could enable. The only ones I'm going to enable are the error protocol and the PDO and SDO configuration. So effectively what this one means is that I'm able to, from Cscape, tell the smart motor what data I want to exchange using PDOs. That's very handy. Okay, so that's the only 2 I'm going to configure on this page. And just like the master, there are several other pages to configure. So nothing here on device type, that's just informational. Special function objects, there's nothing to configure here as a slave. For the master, we had to configure sync As a slave, we don't have to configure sync. So that's nothing to do there either. Error control object, well, that's already set up because our wizard set it up for us. So we're generating heartbeats every 500 milliseconds, and we're checking to make sure the master, as node 127, has sent us a heartbeat at least every 1000 milliseconds. So that's already done. Nothing to configure under service data objects or SDO messaging. Now let's go to the PDOs and take a look at that. All right, so under the transmit PDOs, we'll start there. We had said in our wizard configuration we wanted 2 transmit PDOs, and there they are. All right, so let's go ahead and start from there to add the details as to what motor parameters we want to transmit from the motor back to the OCS. So let's start with the first PDO message. Now, every PDO message can have as much as 8 bytes of data in it. Okay, so as long as we keep our data below 8 bytes, we're good to go. So let's start with the first PDO. Again, this is data that the motor is going to transmit, and ultimately it's going to be received by the OCS in a %R register. So we highlight the first PDO and hit add entry. And now, because we are talking about our smart motor, we can hit the set from EDS button, and we can browse all the motor data that's available for us to transmit back to the OCS. So we're going to start with our status word, which is 6041. That's the hex address. So let's select that. We'll note that that's an unsigned 16-bit value. So we need to make sure that that matches here, and we can say OK. The next one we're going to add, in my case, I'm going to choose the current mode of operation that the motor is in, because we want to verify that it's in positioning mode or find home mode, whatever the case may be. And so that is parameter 6061. So we got to scroll down a ways for that. Up, I went a little too far. 6061, there we go. We have to note that that is a signed 8-bit value. All right, so we need to change this to signed 8-bit value. And now we have configured this PDO in terms of what data is being transmitted. Okay, next I'm going to go ahead and do the same thing for the second PDO, and I'll do this fairly quickly. We're going to add an entry. This time we're going to add the actual value of the position. So what position is the smart motor at? That is 6064. So we'll scroll down for that. Got it. Notice that that is a signed 32-bit value. So we have to set signed 32. There we go. And then the final one we're going to send as part of our demonstration today is we're going to send our actual velocity, which is 6044. And we'll go here and notice that is a signed 16-bit value. So again, the key here is we pick the data that we want and we make sure that the format is appropriate. Okay, so we've done that. So this is the data that's going to be broadcast through a PDO message back to the OCS. So now we need to go back to the OCS, which is the master, and go to its receive PDOs and configure where in OCS memory we're going to map this data coming in from CANopen. So we have to start by adding receive PDOs. And when we hit the add entry button, we get a choice of which one we want to add. So what we're seeing here is the master itself, the OCS itself, is going to be transmitting 2 PDOs. We don't want those. And the slave is going to be transmitting 2 of its own. So that's what we want, is the first transmit PDO from the slave is going to correlate to the first receive PDO with the OCS. Now, don't let this 2 here fool you. This does not indicate node number 2. It just indicates that the slave is second on the list after the master. So again, don't let that fool you. I'll hit select here, and then I'll add the second one. Again, I'm interested in the other PDO. Okay, then I'll go ahead and one by one map where the data coming from the CANopen slave from the smart motor is going to end up in OCS memory space. So I highlight the first receive PDO because we're the master receiving the data. I hit add entry. Now, We don't use the Set from EDS button when we're just mapping data back into the OCS. All we really have to do is type in the register address where we want the data to come in and then make sure we get the type right. So the first thing that's coming back in that first PDO is the status word, which is coming back in unsigned 16-bit format. And I'm going to choose to receive that data into register 1001. So that's all I have to do is type in register 1001 and make sure the format is right. And for the second parameter that's coming in that PDO, that is our mode of operation display, which is a signed 8-bit value. So I'm going to go ahead and put that into %R1002 and make sure that I have signed 8-bit selected here. Hit OK, and then I'm just going to finish up this receive PDO as follows. So I'll add the entry here. My actual position is a 32-bit value. I'll go ahead and put that into %R1005. I can put it wherever I want it as long as it doesn't conflict with anything. That's going to be an unsigned 32-bit. And then the final one I need to add is the actual velocity that's coming in as a 16-bit unsigned. I'm going to put that into %R1007, and 16-bit unsigned is correct. Okay, so that's how we had to configure data being transmitted by the slave and received by the OCS as master. Now we need to go the other direction, right? We need to transmit data from the OCS and we need to send it to the slave. Okay, so let's start on the slave side. Okay, that'll show us the particular data that we want to transmit to it. So let's go to receive PDO on the slave side, hit add entry, and select the master's first transmit PDO. We'll do the same for the second of the master's transmit PDO. All right, then we'll determine what data we want to receive in to the slave, to the motor. All right, so what we're going to do is, the first thing we're going to receive in is the control word, okay? So we're going to set from EDS, and we're going to find the control word, which is 6040 unsigned 16, okay? So that's done. Next, we're going to configure the mode of operation, the one that's being commanded to the motor. So that's 6060, so we got to scroll down for that one. Okay, there we go. And that is a 8-bit signed value. Okay, signed 8-bit value. Next, we're going to go to the second PDO. Now, notice that on each of these PDOs, I've been way below 8 bytes of data. I haven't filled up those PDOs, but I just wanted to get a couple PDOs established, get some data in them, and I've got room to add more later if I need to. Okay, so let's configure the second receive PDO on the motor side. The next piece of data we want to receive from the OCS is the target position. Where do you want us to move to? That is 607A. And again, the reason I know these addresses is because I looked it up in the user's manual. So always have your user's manual handy. That's a signed 32-bit value. And that, of course, is the user's manual for the SmartMotors, what I'm talking about here. Okay, and then finally, we're also going to receive in our velocity, our profile velocity, which is 6081. Okay, got it. 6081, and that is unsigned 32. Let's make sure we have unsigned 32 configured, and there we go. So this is the data we're receiving in from the OCS that tells the motor where to go, right? Well, how fast to go, what position to go to, those sorts of things. So the final piece of the configuration here, finally, is I'm going to the transmit PDO of the OCS to configure which registers effectively the data that I just configured in the slave is going to originate from. Okay, so I select the first transmit PDO for the master, and this is the control word, unsigned 16-bit. I'm deciding as part of my application network map, I'm going to have this transmitted from register 1011. Okay, and then I'm next going to send my mode of operation, which is unsigned 8-bit. I'm going to, it's a signed 8-bit. I'm going to go ahead and originate that from %R1012. Okay, And then next, I've got our next two pieces of data to send from OCS to the motor, and that is the target position where I want the motor to move to. Okay, and I'm going to have that, which is a unsigned 32-bit. I'm going to have that originate from our 1013. And then finally, I'm going to send the profile velocity, or the velocity command, which is unsigned 32. I'm going to send that from %R 1015. There we go. Okay, so now we're basically configured. And yes, that was a fairly long process, but keep in mind that if you just take it kind of very, I guess, very systematically, it's not quite as bad as it looks. It's really just a matter of following the steps in order. There's one last thing I'm going to do, and that is I'm going to go back up to the master configuration, and then under the error control object, I'm going to make sure that my heartbeat monitoring is the way I want it. So I'm generating a heartbeat every 500 milliseconds. At the time we configured this, there was no slave. Now there is, but I don't want to monitor the slave heartbeat every 500 milliseconds. I want to modify it I want to monitor it every 1,000 milliseconds instead, right? Because if it's a little bit late, I don't want to throw a flag. Okay, so now I'm basically done with the configuration. So again, that's the process to go through for a smart motor. If you've got a positioning application, you can follow the same steps. Now, I'll show you another option, okay? And that is, we absolutely can make available to you sample programs pre-configured with not only some configuration in there that you can modify in some cases, but also with plenty of logic already created as well. So now I'm going to go ahead and minimize the program I just created, and I'm going to show you an application that was previously created that you can download if you've got a smart motor application with an OCS as a good starting point for your application. Now, I'm not going to go through step by step and show you what all these different pieces of logic do. I'll just kind of quickly walk through it for you. Okay, so currently we're looking at an initialization section where we take care of some housekeeping items when we initialize. We've got a CANopen section where we've got the standard state machine for CANopen that every CANopen SmartMotor and CANopen servo drive is going to follow. We also, in this section of code, are giving you the ability to send and receive SDOs, so that if you have a parameter you want to change from the screen of the OCS just occasionally, you could do that. And then we've also got logic in here that's decoding the status information coming back from the OCS on CANopen, so you always know the status of the CANopen network. The main section would be where you would put your logic. We've also got a change mode routine. Maybe you're going to have an application where you're always only in positioning mode with your smart motor, but you might have a find home routine. You might need to change into velocity mode or something. If that's the case, you will need to change modes. So that's why this logic is here. There's an enable drive section. That's to make sure that, of course, if you want to move a motor, you're going to have to make sure that it's enabled. So this logic takes care of that in a systematic fashion. There's a find home routine that you can take advantage of. There's logic in here for performing absolute moves, and then there's also logic in here for jogging. So everything is very well documented. You can take a look at it if you download this code. All right, let's do a quick bench demonstration to show you what things look like on the bench. Okay, so what I have here is this demo program that I showed you in Cscape just a minute ago, just in a very simplified form. So here on this screen, we can very easily move our smart motor. You can see over here I have my smart motor connected over CAN2, which is CANopen. And then I have my target position, which currently is set for 4,000 counts. Now, this particular smart motor has 2,000 steps per revolution, and its default acceleration, which I haven't changed, is 500 pulses per second per second. So that's what we're dealing with here. So I'm going to set the Well, the target position is already set to 4,000, which should be 2 revolutions. If I start the move, you can see I moved 2 revolutions. If I go to a target of 0, I should move back 2 revolutions, which I do. If I go to, 100,000 counts, I think that's 100,000, it is. Now, obviously, I'll be moving 50 different revolutions, all right, and moving a little bit quicker because I got past the acceleration time there. Actually, that was 1,000,000 counts, so that was 500 revolutions. I typed in an extra 0 there. Okay, so you can see that's, the simple demonstration I'm doing here for simple positioning. All right, now in addition to this screen, which is just to kind of help you test your result, there's also a detailed screen here that you can take a look at. Now, what's useful about this detailed screen is it shows you the current state of the network, okay? It also allows you to, it kind of breaks down the status word that's coming back from the motor, and it gives you the ability to read and write SDO messages by demand, okay? By typing in the index, or where the data is located in the map, the parameter map inside the SmartMotor, and then reading the result and getting the feedback there. So in this case, I had read the acceleration, the default acceleration for this SmartMotor, because I was curious what it was set at. That's the parameter there, 6083. It came back with a hex value of 1F4, which I believe corresponds to 500 pulses per second. And you also have the ability to write SDO data as well. So that's all there for your convenience. And then there's also another screen that provides you all the status information that's been decoded, along with, some of the parameters we're exchanging with the SmartMotor in this case. Okay, so this is a demo program which I would definitely encourage you to download if it is something, a type of application you're looking to do at any time soon. All right, so that's effectively what I wanted to show you today. So this is the point of the program where I remind you that we're here every Tuesday at 2 o'clock, either fully live or with a pre-recorded video. We love it when you watch on replay and post your comments in the comment section. We love to see the comments, and you can also post your questions there as well so we can get those answered. And we do a pretty good job of getting those answered pretty darn quickly. So again, as I've been doing for this calendar year, we're celebrating our 10th anniversary of Horner Lighting Group products, and there's lots of great Horner lighting videos on our YouTube channel along with our automation content. And then next week, we are covering a fun topic. So I'm going to be demonstrating and showing you some very cool satellite communications with an OCS. Now, when we talk communications on this channel, we're often talk about moving bytes and megabytes and kilobytes and trying to get as fast and as much data exchanged as possible and as efficiently as possible. When you're talking satellite communication, you're managing every single byte. So that's what we're going to be showing you next week. Satellite communications using a Horner OCS. Thanks for joining this week, and we look forward to working with you next week. Everybody, let's all get out there and do us some good.